the light entering your eyes. When you look at the Andromeda galaxy, left its source 2.5 million years ago, before the first humans existed, before stone tools, before anything on Earth could look up and wonder what that smear of light was.
Subscribe, there's a new one every few days. Welcome to White Space. No rush, just the cosmos. Stand somewhere quiet and look up. On a clear night away from the glow of cities, you can see roughly 5,000 individual points of light with the naked eye. That number feels vast until you learn what it actually represents, a tiny fraction of one arm of one galaxy, in a universe that contains somewhere between 1 and 2 trillion galaxies. We are not standing at the edge of something grand, looking in. We are embedded inside it, near the middle of nowhere in particular, trying to understand a structure so enormous that our instincts for scale are simply the wrong tool for the job. To begin to reason about the cosmos, astronomers had to invent new units of measurement. The kilometer, fine for mountains, rivers, continents, becomes meaningless when the nearest star beyond our sun is about 40 trillion of them away. So astronomers first reached for the astronomical unit, the average distance from Earth to the sun, roughly 150 million kilometers, useful inside our solar system. The outermost planet, Neptune, orbits at about 30 astronomical units. The inner edge of the Oort cloud, that vast shell of dormant comets surrounding the Sun, begins at perhaps 2,000 astronomical units and extends perhaps 100,000. But even that is nothing. Beyond our solar system, the unit of choice is the light year, the distance light travels through a vacuum in 1 year. Light moves at approximately 300,000 kilometers per second, which means a single light year equals roughly 9.5 trillion kilometers. At that rate, light leaving our nearest stellar neighbor, Alpha Centauri, takes just over 4 years to reach us. The Orion Nebula, a famous star-forming region visible as a faint smudge to the naked eye in the Sword of Orion, sits about 1,400 light-years away. The center of our own galaxy, the Milky Way, lies roughly 26,000 light-years from Earth. And the Andromeda galaxy, our largest and nearest galactic neighbor, sits at about 2.5 million light-years. These numbers, stacked one on top of another, begin to hint at the true scale. But they are still barely a beginning. Astronomers studying the largest observable structures need yet another unit, the megaparsec, equal to roughly 3.26 million light-years. And it is in megaparsecs that the true architecture of the universe begins to reveal itself. The cosmos is not a uniform fog of matter. It is not a smooth, featureless soup. At the largest scales, the universe is organized into an extraordinary web-like structure, an interlocking system of filaments, sheets, nodes, and voids that looks, in three-dimensional maps, uncannily like the inside of a sponge or like neurons in a brain. Astronomers call this the cosmic web, and understanding it is one of the central achievements of late 20th and early 21st century cosmology. The story of how we discovered this structure is inseparable from the story of how we learned to map the sky in 3 dimensions. For most of astronomical history, catalogs of objects were purely 2-dimensional, position on the sky, but no depth. The breakthrough came when redshift surveys allowed astronomers to estimate the distance to thousands of galaxies simultaneously. When plotted in 3 dimensions, these surveys revealed something nobody had expected to see so clearly. Galaxies are not distributed at random. They cluster into chains and sheets that stretch across hundreds of millions of light years, separated by enormous empty regions where galaxy counts fall to a tiny fraction of the cosmic average. Those empty regions are called voids. They are not truly empty. Even the most desolate void contains a scattering of galaxies, but their density can be 10 times lower than the cosmic mean.
Some voids span 100 to 300 million light-years across. The Boötes void, discovered in 1981, measures roughly 330 million light-years in diameter and contains almost nothing. Standing inside it, if such a thing were imaginable, you would see a sphere of night nearly devoid of galaxies in almost every direction. It would be among the loneliest vantage points in the known universe. Between the voids stretch the filaments, long, tendril-like concentrations of dark matter and gas, threaded through with galaxies and galaxy clusters. These filaments can extend for hundreds of millions of light-years. Where multiple filaments intersect, they form dense nodes, galaxy clusters, and superclusters, the most massive gravitationally bound objects in the universe. A galaxy cluster may contain hundreds or even thousands of individual galaxies, all orbiting a common center of mass within a shared envelope of superheated gas. The Coma cluster, one of the most thoroughly studied, sits about 320 million light-years away and contains over 1,000 large galaxies. The Perseus cluster, another dense concentration visible across a wide range of wavelengths, sits roughly 240 million light-years from us and emits enormous quantities of X-rays from gas heated to tens of millions of degrees. These objects are not just collections of stars. They are the largest bound objects in the cosmos, islands of organized matter at the junctions of the cosmic web. Superclusters are the next level up, though they are not bound in the same sense as clusters. They are more like extended overdense regions, zones where the cosmic web piles up into flat sheet-like walls. Our own galaxy, the Milky Way, belongs to the Local group, a modest collection of about 50 galaxies dominated by the Milky Way and Andromeda. The Local group, in turn, lies near the edge of the Virgo supercluster, which contains thousands of galaxies spread across about 110 million light-years. And the Virgo supercluster is itself only one filament of a larger structure. The Laniakea supercluster, whose full extent reaches 500 million light-years. At even larger scales, structures have been discovered that strain the standard models of cosmic evolution. The Sloan Great Wall, identified in the early 2000s using data from the Sloan Digital Sky Survey, stretches roughly 1.4 billion light-years and represents one of the largest known structures at the time of its discovery. More recently, the Hercules Corona Borealis Great Wall has been identified at a distance of around 10 billion light-years, with an estimated extent of more than 10 billion light-years across. This structure, if confirmed, is so large that it poses a genuine challenge to the cosmological principle, the assumption that on the very largest scales, the universe should look the same in every direction and from every location. The cosmological principle is not just a philosophical preference. It is a working assumption embedded in the mathematics of modern cosmology, and it has enormous explanatory power. The principle holds that the universe is both homogeneous, the same composition everywhere, and isotropic, the same appearance in every direction. Observations confirm this, but only above a threshold of roughly 300 to 500 million light-years. Below that scale, structure reigns. Above it, the cosmic averages level out. Structures like the Hercules Corona Borealis Great Wall complicate this picture significantly. A structure 10 billion light-years across is not merely large. It is so large that it should not, according to standard theory, have had time to form in the 13.8 billion years since the Big Bang. Gravity-amplifying initial density fluctuations can build galaxy clusters in a few billion years. It cannot easily build a coherent structure spanning nearly the entire visible universe. The discovery forces theorists to consider whether the standard picture is incomplete, or whether what we are detecting is something other than a genuine gravitationally coherent structure. The framework for understanding how structure forms at all involves a component of the universe that has never been directly observed: dark matter.
Its existence was first seriously proposed by Swiss astronomer Fritz Zwicky in the 1930s, when he noticed that the galaxies in the Coma cluster were moving far too fast to be held together by the visible matter alone. The cluster should have flown apart. Something invisible was providing the gravitational glow. Decades later, Vera Rubin and Kent Ford showed the same thing for individual spiral galaxies. The outer stars orbit too fast. Whatever holds them in is not stars or gas. It is something invisible, something that does not emit, absorb, or scatter light, but which possesses mass and therefore gravity. Today, cosmologists estimate that dark matter constitutes approximately 27% of the total energy content of the universe. Ordinary matter, atoms, stars, gas, everything we can see or touch makes up only about 5%. The rest, roughly 68%, is something stranger still, dark energy. But we will return to that dark matter's role in shaping the cosmic web is decisive. In the early universe, matter was distributed nearly uniformly with only tiny quantum mechanical fluctuations in density variations of about 1 part in 100,000. Without dark matter, these fluctuations could not have grown fast enough to produce the galaxies and clusters we see today. The gravitational pull of ordinary matter alone would have been too weak. Dark matter halos growing from those tiny fluctuations acted as seeds and scaffolding. Ordinary gas fell into them, cooled and fragmented into stars. Galaxies formed inside dark matter halos. Galaxy clusters formed where dark matter was densest. The cosmic web we observe today is in a very real sense the fossil of dark matter's gravitational history. Computer simulations that include dark matter reproduced the observed cosmic web with striking fidelity. The Millennium simulation, the Illustris project, the Eagle simulation, these enormous computational efforts begin with initial conditions derived from observations of the early universe and step by step model gravitational collapse, gas cooling, star formation, and feedback from supernovae and black holes. The results match what we observe with remarkable precision. When dark matter is removed from the simulations, the web collapses into a much smoother, less structured distribution that looks nothing like the universe we inhabit. How do we know the early universe was nearly smooth? By observing it directly. The cosmic microwave background radiation, the CMB, is the oldest light we can detect. It is not light from stars or galaxies. It is light from the early universe itself, from a moment approximately 380,000 years after the Big Bang, when the cosmos had cooled enough for hydrogen atoms to form and the universe to become transparent. Before that moment, every photon scattered off free electrons almost immediately. The universe was opaque like a dense fog. When atoms formed, the fog cleared, photons streamed free. Those photons are still traveling today, diluted and cooled by 13 billion years of cosmic expansion into microwave radiation at a temperature of just 2.725 degrees Kelvin, barely above absolute zero. Maps of the CMB, constructed by the COBE, WMAP, and Planck satellites, revealed those primordial fluctuations in exquisite detail. The temperature variations across the sky are real but tiny, about 100 millionths of a degree. The pattern contains information about the composition of the early universe, the speed of its expansion, and the geometry of space itself. It is, in a very real sense, a baby photograph of everything that exists. The CMB also marks a boundary. Beyond the surface of last scattering, the shell from which those photons originated, lies a region we cannot see with any electromagnetic signal. The universe was opaque before that moment. Whatever happened in those first 380,000 years is hidden from direct observation. We can infer it from what came after and from the physics we understand, but we cannot look at it the way we look at a galaxy or a nebula.
There is a literal horizon to our electromagnetic view of the cosmos. This observational horizon is related to, but distinct from, the edge of the observable universe. The observable universe is bounded by the distance light could have traveled in the age of the universe, adjusted for expansion. The radius of the observable universe is approximately 46 billion light-years, not 13.8 billion, as one might naively suppose, because space itself has been expanding while the light was in transit. Galaxies we observe at the edge of our observable universe were perhaps a few billion light-years away when their light left them, but they now sit tens of billions of light-years away, carried by the expansion of space. Crucially, this is not the edge of the universe. It is the edge of our view. Beyond it, the universe almost certainly continues. How far, we do not know. If the universe is infinite, if it extends without boundary in all directions, then there is no center, no edge, just more of the same kind of structure we see around us, with different specific arrangements of galaxies, different specific planets, but the same physical laws. But there is a tantalizing alternative. The universe might be finite but unbounded, the same way the surface of the Earth is finite in area but has no edge. You can walk in one direction indefinitely on Earth and return to your starting point without ever hitting a wall. A finite universe could in principle have a topology that loops back on itself in 3 dimensions. One candidate is the 3 torus, a geometry where space wraps around in all 3 dimensions simultaneously. Imagine a video game where your spacecraft exits the right side of the screen and reappears on the left. Now extend that to all 3 spatial dimensions simultaneously. A spacecraft flying in one direction long enough would eventually return to its origin. Observations of the CMB offer a potential test for this kind of topology. If the universe is a 3 torus with dimensions smaller than the observable universe, we should see specific repeating patterns in the CMB, matched circles on opposite sides of the sky, where we are looking at the same region from opposite directions. Several research groups have searched for such patterns. The results are inconclusive but not empty. Some analyses have found statistical anomalies in the large-scale CMB, a deficit of power on the largest angular scales, absences in the pattern of temperature fluctuations that should be present if space extends infinitely but are not clearly present in the data. This is not a proven result, but it is a genuine puzzle that continues to motivate research. What does seem secure from multiple lines of observation is that the universe, at least locally, is geometrically flat. Flat in this context does not mean two-dimensional. It means that the rules of Euclidean geometry apply, parallel lines remain parallel indefinitely, the angles of a triangle add up to 180 degrees. A positively curved universe like the surface of a sphere, but in 3 dimensions, would eventually cause parallel lines to converge and triangles to have angles summing to more than 180 degrees. A negatively curved universe would cause them to diverge. The best current measurements constrain the spatial curvature to within a fraction of a % of perfectly flat. But flat and infinite are not the same thing. A cylinder is flat. You can draw straight lines on it that obey Euclidean rules. But it is finite in one direction. A 3 torus is flat in all 3 directions but may be finite. The flatness of space tells us about local geometry. It does not rule out a finite global topology. The universe can be flat and still loop back on itself. Whatever its topology, the universe is not the same color in all wavelengths. This brings us to one of the more unexpected questions in astronomy. What color is the cosmos? The answer depends on what you mean by color. Human color vision operates over a narrow slice of the electromagnetic spectrum, covering wavelengths from roughly 400 to 700 nanometers. The full electromagnetic spectrum extends from gamma rays at the high energy end with wavelengths smaller than an atomic nucleus to radio waves at the low energy end, with wavelengths that can be larger than a building.
Visible light occupies one part in roughly a million of the accessible electromagnetic range when plotted on a logarithmic scale. This means that the universe we see with our eyes is a fantastically narrow window onto a universe that broadcasts information in every wavelength simultaneously. The dominant source of light in the universe is stars. Stars power almost everything visible in the cosmos. Planets reflect starlight. Nebulae absorb starlight and re-emit it, or scatter it, depending on their composition and temperature. Hot gas clouds in star-forming regions are ionized by radiation from nearby young massive stars and glow in emission lines, primarily the red light of hydrogen's Balmer series. Cooler molecular clouds absorb starlight and re-radiate it in the infrared, invisible to the human eye but detectable by instruments aboard modern telescopes. The light produced by stars spans a wide range of colors, and which color dominates in a given region of a galaxy tells you something about its stellar population. Young, massive, hot stars, the ones that burn brightest and die fastest, emit intensely in the ultraviolet and blue. They live for millions of years rather than billions, concentrating in the spiral arms of disk galaxies where gas supplies constantly trigger new formation. Old, lower mass stars, the red giants and orange subgiants that have been burning steadily for billions of years, dominate the dense central bulges of spiral galaxies and the elliptical galaxies that contain little remaining gas. A galaxy's color is a map of its history. When astronomers average the light from all the galaxies in the observable universe, weighting by the actual number of photons emitted across all wavelengths visible to human eyes, they arrive at a color that is neither the deep blue of young stellar populations nor the warm orange of ancient ones, but something in between, a pale, slightly beige white. The color has been informally called cosmic latte. It represents the average light of all the stars that have ever existed in the observable universe, weighted by their current luminosity. But this visible light average is not the whole story. The universe is bathed in the CMB, whose peak wavelength falls in the microwave, invisible to human eyes. The CMB carries far more photons than all the starlight combined. If you could somehow see it, it would be the dominant feature of the sky in every direction. A dim, uniform glow corresponding to the red of radiation emitted at temperatures around 3000 degrees Kelvin and since redshifted into the microwave. In terms of raw photon count, the universe's true color is microwave red or deep infrared light that our eyes cannot register at all. There is something humbling in this. The universe's most pervasive radiation is invisible to us. The glow of the Big Bang's aftermath, still filling every cubic centimeter of space, is broadcasting information that only radio and microwave instruments can detect. We are surrounded by light we cannot see, bathed in a signal we cannot feel, occupying a universe that broadcasts the majority of its information outside our biological range of perception. The question of how the universe came to be organized, how it grew from an almost featureless early state into the structured cosmos we inhabit, is intertwined with questions about entropy, the tendency of physical systems to move toward disorder, toward states that require less information to describe. Entropy is one of the deepest concepts in physics, and its behavior in the universe is among the most profound unsolved questions in science. In everyday experience, entropy means something close to mess. A drop of ink spreading through a glass of water increases entropy. A shuffled deck of cards has higher entropy than one ordered by suit and rank. The second law of thermodynamics states that in any closed system, entropy can only stay the same or increase over time. The universe runs toward disorder. The physicist Ludwig Boltzmann, working in the second half of the 19th century, gave entropy a statistical foundation. He showed that entropy is a measure of the number of microscopic states consistent with a given macroscopic description. A tidy room can be arranged in relatively few ways while still appearing tidy.
A messy room can be arranged in astronomically more ways. The second law is, in this view, not a fundamental prohibition, but a statement about probabilities. Going from high entropy to low entropy is not impossible, just fantastically unlikely. Boltzmann's insight opens a strange door.
If entropy is statistical rather than absolute, then in a sufficiently old universe, random fluctuations could, in principle, produce any configuration, including a low entropy configuration that resembles an organized cosmos. Given infinite time and an infinite system, such fluctuations would occur. A universe like ours, full of structure and complexity, might be the result not of a special initial condition, but of an extremely rare fluctuation in an eternal, high entropy background. The French mathematician Henri Poincaré had shown years earlier that certain dynamical systems will eventually return arbitrarily close to any configuration they have previously visited, given enough time. This is the Poincaré recurrence theorem for a gas of particles in a box. This means that after an enormously long interval, the gas will spontaneously return to being compressed into one corner, reversing what looked like an irreversible spread. The time scale involved is incomprehensibly large. For a system of even a few dozen particles, recurrence times exceed the current age of the universe by hundreds of orders of magnitude. But the principle holds, applied to cosmology, recurrence, and entropy fluctuations become the basis of some speculative but serious proposals. If the universe is eternal and if entropy fluctuations can produce temporarily low entropy regions, then perhaps what we call the Big Bang was simply a fluctuation, a spontaneous organization of a region of high entropy space into a low entropy initial state that then evolved into the universe we observe. This is not a fringe idea. It has been taken seriously by physicists, including Boltzmann himself, and, more recently, by a number of researchers working at the intersection of statistical mechanics and cosmology. The difficulty is explanatory. Fluctuation cosmologists tend to predict that observers should find themselves in the smallest possible low entropy region consistent with the existence of their observations, a single brain fluctuating into existence with apparent memories of a past that never happened, rather than an entire galaxy full of real history. The fact that we observe a coherent large-scale cosmos argues against simple fluctuation interpretations and in favor of something that produced a genuinely very large, low-entropy initial state. What that something was is the central question of early universe cosmology. To investigate it observationally, astronomers have deployed an increasingly powerful array of instruments. Among the most ambitious is the Euclid Space Telescope, launched by the European Space Agency in July 2023, and now operating from a gravitational equilibrium point 4 times farther from Earth than the Moon. Euclid is not designed to produce the most beautiful images, though its images are extraordinary. It is designed to answer a specific set of questions about dark matter and dark energy with an unprecedented combination of precision and scale. Euclid will survey approximately 15,000 square degrees of sky, roughly a third of the entire celestial sphere, and measure the shapes and positions of over 1 billion galaxies out to distances of more than 10 billion light years. It does this in 2 ways. First, by precisely measuring the apparent shapes of billions of galaxies, it can detect the way dark matter bends light paths passing near large concentrations of mass, a phenomenon called weak gravitational lensing. Gravity curves space and light follows the curvature. A galaxy observed behind a massive dark matter concentration will appear subtly stretched or sheared. By analyzing the statistical distribution of these shape distortions across millions of galaxy pairs, astronomers can reconstruct the distribution of mass, visible and dark, across cosmic history. Second, by measuring the three-dimensional clustering of galaxies at different distances, Euclid maps the acoustic oscillations frozen into the galaxy distribution, echoes of sound waves that propagated through the early universe in the first 400,000 years after the Big Bang. These acoustic signatures provide a standard ruler, a known physical scale that appears imprinted in the galaxy distribution at every distance. Comparing the apparent size of this ruler at different distances reveals how rapidly the universe was expanding at different epochs. This expansion history is the fingerprint of dark energy. Dark energy is the name given to whatever is driving the accelerating expansion of the universe. In 1998, two independent teams studying Type I as supernovae as distance indicators made a shocking discovery. Distant supernovae were fainter than expected, meaning they were farther away than a decelerating or even coasting universe would place them. The universe was not just expanding, it was accelerating. The standard interpretation introduced a term first proposed and then famously retracted by Einstein, the cosmological constant, a form of energy uniformly filling space with a negative pressure that drives expansion rather than resisting it. This component now constitutes roughly 68% of the total energy content of the universe. Despite decades of study, we have almost no physical understanding of what it is or why it has the particular density it does. Dark energy is not dark in the same sense as dark matter. It is not a collection of invisible particles. It appears to be a property of space itself, an intrinsic energy density of the vacuum. As the universe expands, the total amount of dark energy grows proportionally with volume, which is precisely what causes the expansion to accelerate. More space means more dark energy, which drives more expansion, which creates more space. The process is self-reinforcing. If it continues indefinitely, the observable universe will eventually become a nearly empty place, with galaxies beyond our local group receding faster than light can cross the gap, invisible and unreachable forever. Euclid's data, combined with results from ground-based surveys and the CMB, will test whether dark energy is truly constant, a cosmological constant, or whether it varies with time, as some theoretical alternatives predict. If it varies, that variation contains clues about whatever physics underlies it. Meanwhile, the James Webb Space Telescope has been transforming our understanding of the early universe through a different approach: direct imaging of the most distant galaxies accessible to observation. Webb observes primarily in the near and mid-infrared, which makes it ideally suited to studying galaxies at high redshift. The expansion of the universe stretches light to longer wavelengths. A galaxy that emitted visible light 10 or 12 billion years ago has had that light redshifted into the infrared by the time it reaches us. Webb's infrared sensitivity allows it to see these distant objects as they were, sharp and clear, in a way impossible for optical telescopes. What Webb has found has, in several respects, surprised theorists. Large, apparently mature galaxies have been found at redshifts corresponding to only a few 100 million years after the Big Bang. These objects are not the chaotic, irregular protogalactic blobs that standard hierarchical models predicted would dominate the early universe. Some show coherent structure, some contain supermassive black holes at their centers that appear far too massive to have grown in the short time available. Some show chemical abundances, elevated proportions of elements heavier than hydrogen and helium that require multiple generations of stellar evolution to produce more generations than seem to fit within the available time. One striking result concerns galaxy morphology, the shapes galaxies take. Earlier observations with the Hubble Space Telescope suggested that galaxies in the distant universe were predominantly irregular, lacking the clean spiral or elliptical structure that characterizes nearby galaxies. Hubble's view was limited by its inability to observe in the infrared and by the lower resolution available at high redshift. Webb's sharper infrared images tell a different story. When researchers classify galaxies at high redshift using Webb data, they find a much higher proportion of spiral structure than Hubble suggested. In some surveys, the fraction of spiral galaxies at early epochs exceeds 50% compared to perhaps 10% in Hubble-based classifications of the same population. This does not mean the galaxies are identical to nearby spirals, but it suggests that disk structure can emerge and stabilize earlier in cosmic history than standard models predict. If early galaxies are more structured, more massive, and more chemically evolved than current models expect, the models need revision. The most likely revision involves the details of how dark matter halos grow, how feedback from star formation and black hole activity reshapes galaxy structure, and possibly how the first stars, the population of extremely massive metal-free stars that formed in the very early universe, seeded subsequent evolution. Webb is not overturning the Big Bang or the standard cosmological model. It is, however, forcing a more careful examination of the baryonic physics, the behavior of ordinary gas, stars, and black holes inside the scaffolding that dark matter provides. Measuring cosmic distances is among the most technically demanding tasks in astronomy, and the methods used reveal much about the nature of what is being measured. The simplest approach works only for the nearest objects, trigonometric parallax, the apparent shift in position of a star as Earth moves around the Sun, providing a baseline for triangulation. This works out to distances of a few thousand light years at most, after which the parallax angle becomes too small to measure. To go farther, astronomers use standard candles, objects of known intrinsic luminosity, whose distance can be inferred from how dim they appear. Lyrae stars and Sepheid variables are among the most important. Sepheids are massive pulsating stars whose brightness oscillates with a period directly related to their intrinsic luminosity, a relationship discovered by Henrietta Swan Leavitt in the early 20th century, while studying photographic plates of the Small Magellanic Cloud. Knowing how luminous a Sepheid truly is, you can infer how far away it must be to appear as dim as it does. Cepheids were the key to establishing the extragalactic distance scale and were the primary calibrators that allowed Edwin Hubble to confirm that the Andromeda Nebula lay far outside our own galaxy. For the most distant objects, beyond the reach of individual stars, the redshift of spectral lines becomes the primary distance indicator. Light from galaxies shows characteristic absorption and emission lines, fingerprints of specific chemical elements at specific wavelengths. When a galaxy is receding, those wavelengths are stretched to longer values by the expansion of space. The greater the stretching, the greater the redshift, and the greater the redshift, the greater the distance. This is the basis for the Hubble law. Velocity of recession is proportional to distance. For nearby galaxies, that proportionality constant, the Hubble constant, is approximately 70 km per second per megaparsec, though there is currently a statistically significant tension between different ways of measuring it, one of the active unsolved problems in observational cosmology. Through these combined methods, parallax, standard candles, surface brightness fluctuations, and redshift, astronomers have built the cosmic distance ladder, a chain of overlapping techniques, each calibrated against the one below it, extending from the nearest stars out to the edge of the observable universe. The result is a map with a defined outer boundary at a radius of roughly 46 billion light-years. Beyond that boundary, photons have not had time to reach us. The universe may extend far beyond, infinitely far, for all we currently know. And what lies beyond? This is where observational cosmology gives way to theoretical speculation, though speculation of a rigorous kind. Several alternative cosmological frameworks have been developed to address questions that the standard Big Bang model leaves open, including the question of what determined the initial conditions of the early universe. One class of models invokes cyclic cosmology, the idea that the universe is not a unique event, but one of a series of cycles each beginning with a high-density state, expanding, cooling, forming structure, and eventually contracting or transitioning into the initial conditions for the next cycle. The ekpyrotic model, developed in the early 2000s by Paul Steinhardt and Neil Turok, proposes that the observable universe exists on a three-dimensional membrane, a brain embedded in a higher dimensional space, and that the Big Bang was caused by the collision of two such brains. The collision compresses matter and energy in the same way a Big Bang does, produces the same large-scale homogeneity, and can generate the primordial density fluctuations needed to seed structure formation. The cycle then repeats when the brains, driven apart by dark energy analogues, eventually collide again. Roger Penrose has proposed a different cyclic framework called conformal cyclic cosmology. In Penrose's model, the universe passes through a series of aeons. Each aeon begins with a low entropy state analogous to the Big Bang, expands and eventually reaches a future state in which all massive particles have decayed and only photons remain. In the absence of mass, Penrose argues, the distinction between past and future becomes irrelevant, conformal symmetry is restored, and the geometry of the far future of one aeon maps smoothly onto the geometry of the beginning of the next. There is no singularity separating aeons, only a mathematical transformation. Crucially, Penrose argues that signatures of the previous aeon should be detectable in the CMB as circular patterns of temperature variation, Hawking points, as they are sometimes called, produced by evaporating black holes in the previous cosmic cycle. Claims of their detection have been made and disputed, and the question remains open. A very different approach begins not with the geometry of space, but with the nature of time. Some theoretical frameworks suggest that time itself is not a fundamental feature of reality, but an emergent property, an approximate description of a deeper structure that is, at the most fundamental level, timeless. Quantum gravity approaches, including loop quantum gravity and some string theoretic proposals, suggest that at the Planck scale, about 10 to the minus 35 meters, the smallest scale at which current physics is meaningful, space and time dissolve into a quantum form of fluctuating geometry. There is no smooth background in which events occur. Events and geometry are the same thing, mutually constituting each other. In this picture, asking what happened before the Big Bang is like asking what is north of the North Pole. The question assumes a structure, a pre-existing time in which the Big Bang occurred, that does not exist at that level of description. The universe does not begin at a singularity within some pre-existing time. It is the emergence of time itself, along with space and matter and energy, from a quantum gravitational state that has no classical counterpart. These ideas remain mathematically incomplete and observationally largely untested. But the situation is changing. The Laser Interferometer Gravitational Wave Observatory and its partners have opened an entirely new window on the universe, detecting ripples in space-time caused by merging black holes and neutron stars. Future gravitational wave detectors, both ground-based and space-based, will push to lower frequencies and greater distances, potentially detecting gravitational waves from the very early universe, waves that would carry information about physics at energies far beyond what any particle accelerator can reach. If the early universe underwent a phase transition, if extra dimensions opened or closed, if it passed through a bounce rather than beginning at a true singularity, gravitational wave detectors may eventually register the evidence. The cosmic microwave background, too, remains a rich source of information yet to be fully extracted. Polarization patterns in the CMB encode information about the very earliest moments of cosmic history. Inflation, the theory that the universe underwent a brief period of exponentially rapid expansion in the first tiny fraction of a second, predicts a specific pattern of polarization called B-mode polarization produced by gravitational waves from the inflationary epoch. Detection of this signature would be among the most important discoveries in the history of physics, direct evidence of what set the initial conditions for everything that followed. What we have learned, after a century of modern cosmology, is that the universe is organized on scales our intuition cannot grasp, using materials our instruments struggle to detect through processes our theories describe only partially. The cosmic web is real and mapped over billions of light years. Dark matter and dark energy are real, in the sense that something is producing their effects, though their physical nature remains unknown. The early universe was smooth, hot, and dense, and from it grew everything we can see. How that early state was itself produced is the frontier on which physics currently stands. There is something profoundly significant about the position in which we find ourselves. We are small organisms on a small planet, orbiting an average star, in the outer disk of an ordinary spiral galaxy in a universe whose age is nearly 14 billion years. Our direct sensory window onto reality spans a tiny range of electromagnetic frequencies, covers only 5% of the universe's actual content, and reaches back only as far as light from 380,000 years after whatever origin our universe had. And yet from this position, from this pale speck in an unimaginable cosmic web, we have mapped the structure of space on scales of billions of light years. We have detected light from the first 380,000 years of cosmic history. We have inferred the existence of invisible matter that outweighs everything visible by a factor of 5. We have discovered that the expansion of space is accelerating, driven by something we cannot name. We are beginning to test, observationally, whether the universe had a beginning at all, or whether it is part of something cyclic, something infinite, something whose nature is still emerging from our instruments and our mathematics. These are not questions about abstract things. They are questions about the ground on which we stand, the time in which we live, the structure from which we emerged. We are, in the most literal sense, asking why the cosmos exists, and finding, with each new instrument and each new dataset, that the universe contains more structure, more mystery, and more information than any previous generation imagined possible. We do not know where that inquiry ends. We have good reason to believe it does not end anywhere we can yet see. The tools we use to probe the cosmos have transformed so rapidly in the last 3 decades that each new generation of instruments arrives to find a landscape already reshaped by the one before. In the 1990s, the most distant galaxies we could study were barely resolved smudges at the limits of Hubble's sensitivity. Their distances were uncertain, their masses were estimates, their internal structure was beyond our resolution. Today, telescopes in space and on the ground observe those same distant regions with a clarity that would have seemed extraordinary to astronomers of a generation ago. And what they see is consistently more complex, more structured, and more surprising than prior theory predicted. The pattern repeats across the history of astronomy. Each time we build a substantially more powerful instrument, we discover that the universe contains more of everything, more kinds of objects, more extreme examples of known phenomena, more structures at scales we had not previously probed. The lesson seems to be that the universe is not running out of surprises. Every time we look more carefully, it shows us something we had not expected to see. Part of the reason for constant surprise is the way we observe the cosmos. Looking outward in space is identical to looking backward in time. Light travels at a finite speed, the fastest speed physically possible, and so the light we receive from distant objects left those objects long ago. When you observe a galaxy 2 billion light years away, you are seeing that galaxy as it was 2 billion years ago, when the universe was about 11.5 billion years old rather than the 13.5 billion it is today.
Observing the large-scale structure of the universe at different distances is equivalent to watching a time-lapse of cosmic evolution, with the most distant objects representing the earliest epochs and the nearest objects representing the present.
This time depth of observation is not a limitation to work around. It is one of astronomy's great advantages. By surveying galaxies at many different distances, many different epochs, astronomers can directly trace how galaxy populations evolve, how clustering changes, how the rate of star formation rises and falls across cosmic history. The peak of cosmic star formation occurred approximately 10 billion years ago, when the universe was roughly 3 to 4 billion years old. At that epoch, galaxies were forming new stars at rates perhaps 10 times higher than in typical galaxies today. Since then, star formation has been declining. The universe is, in this sense, gradually running out of the raw material, cold, dense gas from which stars are made. The decline has not been uniform. Some galaxies exhausted their gas reservoirs quickly, shutting off star formation early and spending the subsequent billions of years as red, passively evolving stellar populations. Others have continued forming stars at modest rates to the present day. Our own Milky Way falls into this latter category, producing perhaps 3 to 7 new solar masses of stars per year, a modest rate compared to the star-bursting galaxies of cosmic noon, but enough to maintain a healthy supply of young blue stars in its spiral arms. What drives a galaxy to stop forming stars? Several mechanisms are likely involved. Feedback from supermassive black holes, located at the centers of most large galaxies, can heat or expel the gas supply when the black hole passes through an active phase. A quasar or active galactic nucleus, radiating so intensely that the energy output rivals or exceeds the combined light of all the galaxy's stars. Supernova explosions from massive stars inject energy into the interstellar medium, heating gas and driving it outward. Gravitational harassment in dense cluster environments can strip gas from galaxies as they move through the hot intercluster medium. The result, across billions of years, is a galaxy population that has slowly been divided into the actively forming and the passively evolving, the blue cloud and the red sequence, as astronomers sometimes call them, with a smaller population of transitioning galaxies caught between. Understanding these processes in detail is one of the central goals of observational cosmology. Surveys like the Euclid mission, combined with ground-based spectroscopic campaigns covering millions of galaxies, will allow statistically powerful measurements of how galaxy populations change across different environments and different epochs. The cosmic web itself may play a role. Galaxies in the dense nodes of the web, in rich clusters and at filament intersections, may quench their star formation differently and on different time scales than isolated field galaxies floating in the voids. The web is not merely a map of where matter is. It is a record of where matter has been, and an environment that continues to shape the evolution of everything within it. There is another dimension to the cosmic web that has only recently come into focus: the warm, hot, intergalactic medium. Much of the ordinary baryonic matter in the universe, ordinary atoms, does not reside in galaxies. It resides in the filaments themselves, in a diffuse gas that has been shock-heated to temperatures of 10,000 to 10 million degrees by the gravitational energy released as matter falls into the cosmic web. This gas emits X-rays and ultraviolet light, and for decades it was predicted by simulations but extremely difficult to detect observationally. Recent X-ray and ultraviolet observations have begun to detect this component directly, mapping its emission in the filaments between galaxies and confirming that a substantial fraction of the universe's ordinary atoms are distributed through this vast invisible reservoir.
The discovery matters for our accounting of matter in the universe.
For years, observers noted that they could not find as many ordinary atoms as nucleosynthesis theory predicted should exist. The universe should contain a certain amount of hydrogen, helium, and trace heavier elements produced in the first few minutes after the Big Bang, but observations of galaxies and intergalactic gas clouds accounted for only a fraction of it. This was known as the missing baryon problem. The warm, hot intergalactic medium appears to be where most of those missing baryons have been all along, strung through the filaments of the cosmic web in a form too hot to form stars and too diffuse to detect without dedicated deep observations. The first few minutes after the Big Bang produced not only baryons, but also photons and neutrinos in specific proportions that can be calculated from nuclear physics and the known expansion rate of the universe. The process is called Big Bang nucleosynthesis, and it produced approximately 75% hydrogen by mass, 25% helium, and trace amounts of lithium and deuterium. Everything heavier, all the carbon, oxygen, nitrogen, iron, calcium, and other elements that make up planets and people, was produced inside stars and distributed into the interstellar medium by supernova explosions, stellar winds, and neutron star mergers. We are, in the most literal sense, made of stellar ash. The verification of Big Bang nucleosynthesis predictions is one of the great successes of modern cosmology. Measurements of the primordial helium abundance in the oldest, least chemically enriched gas in the universe, and of the deuterium abundance in high redshift intergalactic gas clouds, agree with theoretical predictions to within the current observational uncertainties. This concordance, combined with the CMB measurements and the observed large-scale structure, forms the evidential basis of the standard cosmological model. But concordance is not the same as completeness. The standard model has significant gaps. The nature of dark matter, the 27% of the universe's energy budget that is not ordinary baryonic matter and not dark energy, remains one of the most important unsolved problems in physics. Decades of experiment have searched for the most theoretically favored dark matter candidates, weakly interacting massive particles, or WIMPs, which would be produced in the early universe at the right abundance, and would interact with ordinary matter through the weak nuclear force at a rate accessible to direct detection experiments. These experiments, conducted deep underground to shield them from cosmic ray backgrounds, have grown progressively more sensitive over time, expanding their reach by many orders of magnitude. So far, they have found nothing. The absence of a WIMP signal in current generation experiments does not rule out dark matter. There are many other candidates, but it has narrowed the parameter space substantially and shifted theoretical attention toward alternatives, including axions, sterile neutrinos, and various exotic possibilities. Axions are particularly interesting. Originally proposed in the 1970s to solve an unrelated problem in particle physics, the strong CP problem, concerning why the strong nuclear force does not violate a certain symmetry the way it theoretically could. Axions would be extremely light, extremely weakly interacting particles produced in enormous quantities in the early universe. They would not decay, they would not annihilate, and they would cluster gravitationally in halos around galaxies. Several experiments are searching for axions using sensitive microwave cavities that would detect the faint photons produced when axions convert in a strong magnetic field. If axions are found, they would simultaneously solve two distinct problems in physics, which is the kind of discovery that tends to reorganize entire fields. Meanwhile, the tension in measurements of the Hubble constant, the rate at which the universe is currently expanding, has become one of the most discussed problems in cosmology. When the Hubble constant is measured from the CMB, using the standard cosmological model to extrapolate from the early universe to the present,
The result is approximately 67 kilometers per second per megaparsec. When it is measured using local distance indicators, Cepheid variables calibrated against nearby parallax measurements, then used to calibrate type VA supernovae, which can be observed across billions of light years, the result is closer to 73 kilometers per second per megaparsec.
The discrepancy at about 8 to 9% may seem small, but it is statistically significant.
The error bars on each measurement from independent teams using independent methods do not overlap. If both measurements are correct, the standard cosmological model is missing something. New physics at early or late cosmic times, exotic dark energy behavior, additional neutrino species, or interactions between dark matter and dark energy have all been proposed as potential resolutions. None has been definitively confirmed.
These tensions, the Hubble constant tension, the sigma-8 tension in measurements of the amplitude of matter clustering, the anomalies in the CMB on large angular scales are not crises in the sense of overturning the framework. They are anomalies points where the data do not quite fit the predictions, where something in the model may need adjustment. Historically, such anomalies have been among the most productive engines of scientific progress. They force theorists to build new models and observers to design new tests. The anomalies of the 1990s, in particular the failure of the then standard model to match the precise shape of the CMB power spectrum, led directly to the introduction of dark energy as a component of the universe, a prediction confirmed by the supernova observations of 1998. The universe is speaking to us in data, and we are learning with each new generation of instruments to read more of what it is saying. The Vera C. Rubin Observatory, currently completing commissioning in Chile, will survey the entire southern sky every few nights for a decade, accumulating a dataset of 20 billion galaxies and producing a time-domain movie of the variable and transient sky at a depth and cadence previously impossible. The Nancy Grace Roman Space Telescope, NASA's planned wide-field infrared mission, will survey large areas of sky with Hubble-class resolution, enabling statistical studies of weak gravitational lensing across a volume of the universe that no previous space telescope could access. A square-kilometer array, the largest radio telescope array ever built, will detect hydrogen emission from galaxies across cosmological distances, mapping the neutral gas content of the universe through cosmic time and probing the epoch of reionization, the period when the first stars and galaxies lit up the universe and ionized the surrounding intergalactic gas. Each of these instruments will generate data at rates that challenge our storage and computing infrastructure as much as our theoretical frameworks. Machine learning is already being deployed to classify the hundreds of millions of objects that will appear in Rubin Observatory images, to identify gravitational lenses among billions of galaxy images, and to separate cosmological signals from astrophysical foregrounds in CMB maps. The boundary between the instrument and the analysis is becoming as important as the instrument itself. There is something philosophically significant in the trajectory of this enterprise. Humans begin watching the sky from the perspective of a fixed central Earth, with the stars as decorations on a rotating sphere. We now know that Earth is a small, ordinary planet in an unremarkable solar system, at an average location in an ordinary galaxy, which is one of perhaps 1 trillion galaxies distributed through an observable universe whose radius spans 46 billion light-years, in turn embedded within a larger universe, possibly infinite, possibly finite, possibly cyclic, possibly one of many, whose full extent and nature we do not yet know. This demotion of position has not diminished the significance of the inquiry. If anything, it has deepened it. The more we learn about the scale and structure of the cosmos, the more remarkable it becomes that it contains anything at all.
that the initial conditions were such as to allow stars and planets and chemistry and life.
The fine-tuning of physical constants, the fact that slightly different values of the fundamental parameters of physics would produce a universe with no atoms, no stars, no complexity of any kind, raises questions that physics alone cannot fully answer. Some researchers invoke the anthropic principle: we observe the universe to have the properties it has, because universes with different properties would not contain observers. Others propose the multiverse, a vast ensemble of universes with different physical parameters, of which we inhabit one compatible with our existence by selection rather than by design. Others hold that the parameters are determined by deep theoretical principles we have not yet discovered. None of these is a settled resolution. All are live areas of research and philosophical debate. The fact that the question can be asked, that a creature made of stellar remnants, living on a rocky planet, orbiting an average star, can formulate a coherent inquiry into the origin and structure of the totality of everything, is itself extraordinary. It may be one of the most extraordinary facts that exist. We do not know why the cosmos exists. We do not know whether the Big Bang had a cause, whether time had a beginning, whether our universe is unique or one of many. We do not know what dark matter is, or what dark energy is, or whether the universe is finite or infinite. We do not know whether, somewhere in the cosmic web, there exist other minds that have asked the same questions and arrived at different answers. But we are not standing still. The data accumulates, the instruments improve, the theoretical frameworks sharpen with every measurement of the CMB, every redshift survey, every gravitational wave detection, every image from a telescope aimed at the edge of the observable universe. We add another sentence to a story we did not choose to write but cannot stop writing. The universe is older and stranger and larger than any previous generation imagined, and we are just beginning to understand what it is telling us. Consider what it means to measure the temperature of empty space.
In the 1960s, two radio astronomers working at Bell Labs in New Jersey pointed a horn antenna at the sky to measure a source of microwave noise that was interfering with their communications work. They checked their equipment, cleaned out pigeons nesting in the antenna, and tried every conventional explanation. The noise remained constant in every direction, present day and night, indifferent to the orientation of their instrument.
What Arno Penzias and Robert Wilson had detected was the cosmic microwave background radiation, the echo of the Big Bang, filling the entire observable universe with a uniform bath of photons at 2.7225 degrees above absolute zero. The discovery won them the Nobel Prize in Physics and provided the most direct evidence ever obtained that the early universe was, as theory predicted, hot, dense, and far smaller than it is today. The CMB is the foundation on which modern precision cosmology rests. But it is also a window with a particular kind of limit. The photons of the CMB were last scattered roughly 380,000 years after the Big Bang. Before that moment, the universe was too hot and too densely ionized for light to travel freely. Every photon emitted immediately bounced off a free electron. The universe was opaque. Whatever happened in those first 380,000 years, whatever initial conditions produced the fluctuations we see imprinted in the CMB, is hidden behind an electromagnetic horizon, a wall of ionized plasma before which our photons cannot penetrate. Gravitational waves offer a possible way around this limitation. Unlike light, gravitational waves interact so weakly with matter that they propagate freely even through the dense hot plasma of the very early universe. Gravitational waves produced by inflation or by a bounce or by a brane collision, depending on which early universe model is correct, would still be propagating today,
embedded in a cosmic gravitational wave background, analogous to the cosmic microwave background. Their detection would provide a direct observational handle on physics at energies 10 to 15 orders of magnitude, beyond what any particle accelerator can reach.
The LISA space-based gravitational wave detector, planned for launch in the 2030s, will access frequencies sensitive to a variety of early universe sources. If inflation produced gravitational waves at the predicted level, and if next-generation CMB experiments detect the corresponding B-mode polarization signature, the early universe will speak to us in two independent channels simultaneously.
The possibility of observing the same physical phenomenon through multiple independent messengers, light, gravitational waves, neutrinos, has given rise to the concept of multi-messenger astronomy. The first major example came in 2017, when the merger of two neutron stars was detected simultaneously in gravitational waves by the LIGO and Virgo detectors, and in electromagnetic light across the full spectrum, from gamma rays to radio waves, by dozens of observatories worldwide.
That event confirmed that neutron star mergers are sites of R-process nucleosynthesis, the rapid neutron capture process that produces roughly half of all the elements heavier than iron in the universe, including gold, platinum, iodine, and uranium. Every ounce of gold on Earth was forged in the collision of two dead stellar cores, billions of years before the solar system formed, and scattered across the interstellar medium to be incorporated into the molecular cloud that eventually became the Sun and its planets. Multi-messenger observations of the early universe represent the frontier of this approach. Neutrinos, like gravitational waves, decoupled from the rest of the universe very early, within the first few seconds after the Big Bang, and have been streaming freely ever since. The cosmic neutrino background is predicted by standard cosmology and would contain neutrinos at temperatures of about 1.95 degrees Kelvin, carrying information about the universe before the CMB photons were released. Detection of the cosmic neutrino background is one of the holy grails of observational cosmology. The neutrinos are extremely difficult to detect because they interact only through the weak force and gravity. But several experimental proposals using relic neutrino capture on radioactive targets are in development. The question of why the universe contains more matter than antimatter is another open problem that connects the very early universe to the observable cosmos we inhabit. The laws of physics, as currently understood, apply almost symmetrically to matter and antimatter. Given equal amounts of both in the early universe, matter and antimatter should have annihilated entirely, leaving only photons. Instead, a slight asymmetry, approximately one extra particle of matter for every billion matter-antimatter pairs, survived annihilation and became everything we can see. The origin of this asymmetry is unknown. It requires physics beyond the standard model of particle physics, and identifying what that physics is remains one of the central open problems at the interface of particle physics and cosmology. Experiments studying the properties of antihydrogen and measuring the properties of neutrino oscillations are among those searching for the mechanism. These questions about what dark matter is, what dark energy is, why matter dominates over antimatter, what set the initial conditions of the Big Bang, whether the Big Bang had a predecessor or whether time itself had a beginning, are the deep questions of contemporary physics and cosmology. They are questions that may take generations to resolve. Some may turn out to require conceptual frameworks that do not yet exist. The way general relativity required a conceptual framework that did not exist before Einstein. The history of physics suggests that the biggest advances often come from recognizing that a question has been wrongly framed, that what seemed like a problem within an existing framework is actually pointing to the need for a new one. What is certain is that the universe is stranger, larger, older,
and more intricately organized than any prior generation suspected. It is constructed from materials we cannot see, governed at the largest scales by an energy we cannot identify, and accessible to us through a thin sliver of radiation that our biological sensors can process.
And yet, from this position, this impossibly constrained vantage point on a small warm planet, we have managed to map the geometry of space, decode the composition of the early universe, trace the evolutionary history of galaxies across 10 billion years, and identify the dominant energy components of the cosmos even while remaining unable to observe them directly. The universe does not owe us these answers. It does not arrange itself for our convenience or our comprehension. But it appears to be governed by regular mathematical laws that our minds, products of 4 billion years of biological evolution and a planet that itself formed from stellar debris, are somehow capable of discovering and understanding. That correspondence between the structure of the cosmos and the structure of human mathematics is itself one of the most astonishing facts of our situation. It suggests, though it does not prove, that the universe is in some deep sense comprehensible, that its secrets are secrets waiting to be found rather than barriers forever beyond our reach. We look up from this small world into an enormity we can barely characterize. We detect the echo of a beginning we cannot see. We map structures built of matter we cannot touch. We measure an energy driving everything apart that we cannot name. And we keep asking the question that has been asked in every language and every civilization since humans first tilted their faces toward the stars. Why is there something rather than nothing? Why does the cosmos exist? We do not have the final answer. We may never have it. But we are closer than we were, and the next generation of instruments will bring us closer still. The universe has been speaking for 13 billion years. We have been listening carefully for only a few hundred. There is much yet to hear.